Hi, and welcome to Failurology, a podcast about engineering failures, and sometimes engineering marvels, like this episode. I'm your host, Nicole, and with me again today is Brian, and we're both from Calgary, Alberta. Welcome, Brian.
Thanks for having me again.
So, I went on an overnight backpacking trip this weekend. It was nice to get out of cell service, and it wasn't even that smoky, thankfully. Brian, I understand you've done a lot of hiking.
I've done a little bit of hiking. I've walked from the Mexico-U.S. border all the way up to the Canada border. So that was 2,650 miles.
It's a lot of miles. How long did that take you?
It was about 4.5 months worth of walking. So it looked a lot closer on the globe when I went down there. But
So when I believe they call that through hiking, how much stuff do you bring with you? How often can you refuel?
So I don't actually bring that much stuff with me, but I have quite a bit of backpacking experience. So my base weight are kind of the things that we carry that aren't consumable. So sleeping bags and tents and backpacks and sleeping mats. My base weight is under 10 pounds, so not a lot of stuff. And on the Pacific Crest Trail, which is the trail that I did from Mexico to Canada, we would resupply every 4 days to 7 days.
Well, that's not so bad. So you need to carry almost a week's worth of food, and then you get more food.
Yeah, generally, yeah, a week's worth of food. Say 5 days worth of food, just to play it safe for the shorter ones, and then maybe 8 days worth of food for a longer resupply.
And then you can get water on trail, so you don't need to carry. Water's heavy.
Yeah, water is heavy, and thankfully outside of the really southern parts, water is quite abundant on the rest of the trail.
Oh, that's good. Yeah, because one liter of water weighs 1 kilogram, which is, it's a lot of water. It's heavy. It's a lot of extra weight when you're carrying it on your back.
It definitely adds up. So there were some desert sections where we were carrying 6 to 8 liters of water, just because there was no water between some resupplies. So yeah, it definitely adds up in weight, 10, 15 pounds worth of water.
Wow, brutal.
I was in much better shape than what I am now, and much younger, and probably better looking.
Yeah, I think I'm in good shape, and then I start going uphill, and I realize that I am not in as good of shape as I thought I was, and I don't like hills. I much prefer flat walking.
It happens to the best of us.
Are there a lot of hills on the Pacific Crest Trail?
There are many, many hills. I believe it's 20. It has the elevation gain of 26 Everests, I believe is the number.
Well, obviously not all at once, but is it gradual, or are there really steep sections?
It's pretty gradual. So the Pacific Crest Trail was graded for horses. So the maximum grade's around 5%, which means that when you're going up, you go up for a long time, a couple hours sometimes of going up, and then you hit a pass, and then you go down for a couple hours.
Interesting.
So it's very gradual, but very long.
What would you prefer? Short, straight up, or long, gradual?
I'm not actually sure. I really like going up hills, so I don't have a preference. I like both of those.
I think the gradual will be better. Coming downhill when it's really steep is hard on your knees.
This is very true. Yeah, overall, I think the gradual uphill and downhill is probably the better way. I feel less tired when I do those ones. I've done another longer trail a few years before, the Appalachian Trail, and that goes from Georgia all the way up to Maine. And that one's just over 2,200 miles, and it's got a lot of fairly steep up and downhill sections, and it's fairly rocky, and there's lots of routes. So I didn't make as many miles per day on that trail as what I did on the Pacific Crest Trail, but they were both really, really fun, and they were both fairly long. It took 4.5 to 5 months to finish.
It's a long time. Yeah, I've heard of lots of people breaking it up, so they'll do it in 1 or 2 month sections over a few years, just because, taking 4 months off work is a long time. I was in Ontario recently on vacation, and I did some hiking there on the Bruce Peninsula, and lots of routes, and it's a lot more tricky. You have to pick your foot up a lot higher. And I know that sounds silly, but when you're, I think I did 30,000 steps that day. So, that's a lot of extra work to pick your foot up that much higher. And that was an interesting trail because the total elevation gain was 450 meters. But we got, so you kind of got to the top and walked along. But then once we came back down, it was up, down, up, down, up, down. And so it's like, why do we just keep going up just to go back down again? Why can't we just stay down here?
That sounds like most of the Appalachian Trail.
I don't like hills as much. They're not my thing. Anyways, we should probably get into the engineering news.
This week in engineering news, we are going to talk about sensors in protective clothing that can determine whether the protective clothing is still safe for wear. Over the last month here in Western Canada, we've seen a lot of forest fires, wildfires that are going on in the summer. And one of the things that firefighters need to deal with these forest fires is protective clothing. And over time, due to UV exposure and heat exposure, the protective abilities of the clothing wears out. And that's where Patricia DeLeese from the University of Alberta in Edmonton comes in. And her and her team, they partnered with Davy Textile Solutions, again based out of Edmonton, to develop a sensor that can detect the gradual breakdown of fire-retardant garments from exposure to heat, moisture, and UV light, which seems like a pretty important thing if you're out fighting forest fires. So the sensor, it's a patch that goes on the clothing, so there's no destructive testing that's required for it. And it uses graphene, so a flake substance that's composed of carbon atoms to form tracks on the patch's surface. And when the exposure exceeds a threshold, a track is disrupted and loses electrical conductivity. So we can apply a voltmeter to check the conductivity of the patch, and if it doesn't meet a threshold, then we can determine that the clothing is probably not safe for use in a hazardous environment. So right now it just has a provisional patent, so it's still under development. And the National Fire Protection Association is preparing to change its recommendations on garment maintenance. Current recommendation is to wash garments once or twice a year, but as a result of harmful substances leaching into the fabric, NFPA is looking to change its recommendation to wash garments after each firefighting exposure. This would considerably impact the integrity of the fire-retardant fabric.
Brian, did you know that the NFPA was formed in 1913?
I did not know that it was formed in 1913.
I am fascinated with the National Fire Protection Association. I know that sounds weird, but they have so many cool codes. And I mean, I didn't even know that they covered firefighting garments as a code section. I look at their codes for sprinkler placement, for commercial cooking equipment, fire suppression. Some types of specific buildings have different sections. There's a fire extinguisher section, but they have hundreds of sections in there, or chapters, I guess you could say, in their code. And it's just so interesting. So they have a section on combustible cladding, which I talked about in episode 4 on the Grenfell Tower fire. And they were formed, like I said, I believe it was 1913, shortly after the Triangle Shirtwaist Factory, where really, really poor exiting design and operational layouts limited the evacuation of a large number of factory workers. And unfortunately, a lot of people died. And so out of that, and a number of other factory fires, the NFPA was formed. And they've done a lot of really good things for the industry.
Does tragedy drive a lot of code development? I mean, not just specifically the NFPA, but do disasters drive a lot of, subsequent code development?
As a result of this podcast, I'm learning that tragedy drives just about everything. But I would say, I wouldn't say tragedy specifically, in that it's never anything quite so extreme. So the codes try to cover everything, but there's always holes in them, and not on purpose. It's just that there are. And so eventually something slips through that, and then new sections are made. So I think that the codes and standards people are really good at being proactive, but it's almost impossible to catch everything without writing a code that's so prescriptive that it leaves no leeway for interpretation. You have to be somewhat creative, right?
Yeah, we certainly see that in aviation.
Yeah, tell me more.
Well, as a result of a number of tragedies or airplane crashes or incidents, codes both in the US and Canada have been rewritten to mitigate, what caused that disaster, or to mitigate, a loss of life that occurred, on board an aircraft or when an aircraft made contact with the ground. And a lot of our technological innovations are driven by tragic events that have happened in aviation.
Yeah, I think that's important that they're changing the codes. I just hope that they're trying to change codes before incidents happen. So I'd like us to be more proactive than reactive. And I don't know how, that's not always possible because you can't see everything. You have to basically look at all the ways something could break or fail, or all the ways someone could get hurt or someone could not follow the code, and try to protect against that, which is a really, really hard task.
And there's always gonna be something that you haven't thought of, or there's something that somebody designs around the code to maybe get around a code issue that unfortunately you do wind up having to write into code after the fact or after a tragedy, which is unfortunate.
For sure. And the interesting thing about building construction is every building is custom, really. The codes repeat themselves, the design concepts repeat themselves, but unless you're literally building cookie cutter buildings that are the exact same, no two buildings are the exact same. And so you've got different scenarios and they don't always fit within the code. But all that said, I think the codes writers have done a great job so far. And I would say the bigger risk is people not following the codes.
Yeah, and I think codes have certainly come a long way, in the last 20 years, certainly in the last 50 years. And then sometimes we go back to, old designs or old plans from, the early 20th century. I'm astounded by some of the things that are even in there for design, or what passed as suitable design back then that nobody now would even think about putting into a plan or a design.
Yeah, I have seen some stuff for sure. One thing that I like most about NFPA, and they're not the only ones now, but their code has been available online for free. All you need to do is create a login for several years now. And I like that because, you can write the code however you want, but if you put it behind a paywall, people aren't going to get it, and they're going to hope that they followed it, and things are going to slip through the cracks. And so I think it's important, if you want people to follow the code and you want to enforce the code, it's important to make it accessible. And so I'm seeing a lot more codes now being available online for free, but NFPA has been doing it for years. And I just think that is just a great service that they offer.
Yeah, we certainly spend a considerable amount of money every year on code subscriptions, just to make sure that we're completing our designs as they need to be completed to code standard.
Yeah. So if you want to read more on the fire retardant fabric sensor, check out the link in the show notes or head to failurology.ca. Hey, Brian, what's the first thing you think of when people approach you on the street?
Well, mostly the Audacity.
Isn't that an audio recording program?
It is, but they don't sponsor this podcast. If they did, though, this week's episode of Failurology would be brought to you by Audacity.
Now on to this week's engineering marvel. It's about a man, a plan, a canal. The Panama Canal. One of the largest and most difficult engineering projects ever undertaken. The American Society of Civil Engineers has named the Panama Canal one of the 7 wonders of the modern world. Also on that list is the Channel Tunnel that we covered in episode 20. If you've been following the show, every 10th episode, we're covering a marvel instead of an engineering failure. Just something to mix it up, maybe make the show a little bit lighter. But of course, we like to stay on brand, and so we're going to talk about all of the challenges and difficulties that came along with building the canal. But we look at this overall as a major success for engineering and really for shipping around the world. The Panama Canal is an 82-kilometer canal that connects the Atlantic to Pacific Ocean shipping routes across the country of Panama. It's a major conduit for maritime trade, and it allows ships to avoid the Cape Horn route, which is around South America, or the Bering Strait north of Canada, both of which are longer and more dangerous. Although with the recent ice melting we've been seeing, the Bering Strait is becoming a more viable option nowadays.
Thanks, climate change. The first record regarding a canal across the Isthmus of Panama, and the isthmus is the narrow strip of land, or a narrow strip of land that connects 2 larger land masses. It's like a big land bridge connecting 2 land masses. So the first record we could find for something related to a canal was in 1534 with the intent to ease the voyage of ships between Spain and Peru. Successful canals around the world had been built in the late 18th and 19th century, notably the Erie Canal, which opened in 1821, and the Suez Canal, which opened in 1869. Prior to the Panama Canal being built, the United States constructed the Panama Railroad across the isthmus to facilitate trade between the Atlantic and Pacific ship traffic. So A ship would pull up on the Atlantic side, they'd offload everything on the ship, load it onto railway cars. The train would drive across to the Pacific side, and then they would take everything off the train and load it onto another ship. So it wasn't the most efficient way for goods to get from the Atlantic to the Pacific, but it was much better than going all the way around Cape Horn.
I guess you would only drive to that one side, and then another boat would meet it on the other side and pick up the parts. So I guess you would just have a shorter route. You would just probably go back and forth.
Yeah, you'd have a shorter route, but it's still incredibly inefficient to load a ship up, bring it to the western approach of the Panama Railroad, unload it, load everything onto train cars, and remember this is back in the early 1900s, prior to the early 1900s, so that the trains aren't super powerful. They don't have giant port facilities. Probably a lot of it's done by hand or very rudimentary cranes. So you have to load the trains that go very slow. They're steam driven, for 80 kilometers or 100 kilometers across the isthmus. Then you have to unload everything onto another ship. So yeah, it was an incredibly inefficient way to do things, but it was the best option that they had at the time.
Yeah. So France began work on the canal in 1881, and significant funds were raised by French diplomat Ferdinand de Lesseps as a result of the profits generated from the successful construction of the Suez Canal.
Yeah, so the Suez Canal, and we'll get to this in a little bit. So the Suez Canal was built at sea level.
So no locks.
No locks on this one, just a straight cut that allowed ships to transit.
But the Panama Canal was much more difficult to construct than the Suez Canal due to tropical rainforest, climate, and elevation changes along the route. So de Lesseps proposed a sea level canal similar to the Suez Canal, but during the wet season, the Chagres River can rise up to 10 meters, necessitating the need for locks. The crews dealt with snakes, insects, spiders, yellow fever, and malaria, to name a few, which unfortunately resulted in thousands of worker deaths. Work eventually stopped by the French on the 15th of May, 1889, after they had spent a considerable amount of money, and unfortunately 22,000 workers perished from disease and accidents from the construction so far.
The U.S. eventually took over construction of the Panama Canal from the French and purchased French equipment and excavations, including the Panama Railroad, for, at the time, US $40 million, which sounds like a considerable sum for that period of time. So the US took control of the Panama Canal project on May 4th, 1904, after a number of diplomatic and military actions that may or may not have been completely above board. As Nicole mentioned, there was significant disease that the French workers were faced with malaria and yellow fever and insects and other diseases that we've essentially eradicated now. So at the time, Colonel William Gorgas, the chief sanitation officer for the project, implemented a series of measures to reduce yellow fever and malaria. And these were things like screens and clearing vegetation and getting rid of standing water, things that are fairly common that we take for granted now, but at the time are seen as almost revolutionary things to do. So after a couple of years of work, all the mosquito-borne illnesses and diseases had essentially been eliminated. So the French had originally proposed to build a canal similar to the Suez Canal at sea level. The chief engineer for the project for the US, Chief Engineer John Stevens, recommended a lock system to raise and lower ships. This would create the largest dam, the Gatun Dam, and the largest man-made lake, Gatun Lake, in the world at the time. Unfortunately, this would also require an additional excavation of 130 million cubic meters beyond what the French had already excavated. And at the time, the French had excavated 23 million cubic meters of soil material.
So is that why they didn't do a sea level canal design, was because it was a lot of extra work to cut through? Or was it the fact that the water levels were just really challenging to deal with because you'd get all the rainfall, and then there was periods of rainfall, and then there was periods of drought, and so the water within that cut may have been challenging to manage, or why do you think they didn't do it?
Yeah, I think it was probably a combination of all of those things that you mentioned. So at the time, a lot of the French designers had only visited Panama in the dry season. And during the wet season, the Chagres River can rise up to 10 meters from where it currently stands in the dry season, which is fairly substantial volume of water So yeah, I think it was a water volume issue. The elevation differences between the Atlantic and the Pacific side are two different sea level elevations. There's just a phenomenal amount of dirt that needs to be moved to get a sea level, kind of a sea level to sea level canal, in the same way that the Suez Canal was built, and the engineering technology that's required to build different locks and have holding reservoirs for the water to either go into or to flow from a reservoir. Those are fairly substantial engineering challenges for turn of the 19th century. The current locks that we have are 700 tons each, which is fairly substantial weight, and then also something to manufacture and bring to site and to put in place. At the time that they're building this, we haven't really come into fruition for diesel railway technology or good metalworking. We're dealing with steam bucket loaders and steam shovels that are mounted on railway cars, on steam driven railway cars. So they're trying to build a substantial engineering project with what we would consider I think fairly primitive technology compared to what we currently have right now for road projects and bridge projects and dredging projects, and things that we commonly take for granted they didn't have, or they hadn't been invented yet.
Yeah, I would definitely agree that the technology available was significantly limited in comparison to what we have today. I mean, significantly. I just thought it was interesting because, I follow why the locks are there, but they make the passage every time someone goes through the canal that much more complicated, because now they have to go through the locks, and it's a much more involved process than it had been at sea level. And I'm just curious if there was a way to make it at sea level, and maybe passage would be a lot better, and they could deal with the other problems. But I understand why at the time they didn't. I think it's really interesting how they kind of dealt with the problems that were in front of them.
Yes. So to move all of this dirt, they need to move 130 million cubic meters. They bring in 130 steam shovels that are mounted on railway cars. They have cars that are hauling away rock and spoil, kind of one train per minute, which is fairly substantial. And it's a lot of dirt to move. I mean, even now it's a lot of dirt to move, let alone back in the day moving dirt. So yeah, again, this is a substantial engineering undertaking. And unfortunately, in 1907, Stevens resigns, and he's replaced by U.S. Army Major George Washington Goetheless, a West Point trained leader and civil engineer who has considerable experience in canal building, which is something that Stevens didn't have. Under Goethel's leadership, the project finishes 2 years ahead of schedule.
I can promise you that never happens.
I can also
only time in history.
This never happens. Yeah, it's
a
one-off history event. We blew it all on the Panama Canal, so hopefully it was worth it. So the canal opens on August 15th, 1914.
Brian, that's the same day this episode comes out, August 15th.
But not of 1914.
Well, correct. There was no computers in 1914. They didn't have podcasts back then.
Yeah, they just had phonograph.
The radio. We could be on the radio.
All told, the U.S. spends $500 million in 1914 to build the Panama Canal, which in 2020 dollars is $12.9 billion, which is more money than I have right now.
Same. Only by a little, though.
Just a bit. So the U.S. controls the canal until 1977, and then shares the canal with Panama until Panama fully takes it over in 1999.
I'm glad they have full control of it. I think that's important.
They did raise tariffs quite a bit.
Yeah, they did. I'm going to talk about the tariffs a little bit. But I first want to talk about passage. What exactly is involved in the canal? I think that'll help make a little more sense of it. There is a map on the website. One, a visual map of the land, and it shows the path of travel, but then also a map that shows kind of the steps that you follow to get through the canal when traveling from the Atlantic through to the Pacific. While globally, the Atlantic Ocean is east of the isthmus and the Pacific is west, the general direction of the canal passage from the Atlantic to the Pacific is northwest to southeast because of the shape of the isthmus at the point the canal occupies. As I said, there's a map if you want to check it out on the website, failureology.ca. The canal consists of artificial lakes, several improved and artificial channels, and 3 sets of locks. There are 6 locks in total, but they're broken up into 3 sets. An additional artificial lake, Alajuela Lake, known during the American era as Madden Lake, acts as a reservoir for the canal. The layout of the canal, as seen by a ship passing from the Atlantic to the Pacific, is as follows. From the formal marking of the Atlantic entrance, one enters Limon Bay, a large natural harbor, and the entrance runs about 8.9 kilometers. It provides a deepwater port with facilities like multimodal cargo exchange, to and from train, and the Cologne Free Trade Zone. Then there's a 3.2 kilometer channel which forms the approach to the locks from the Atlantic side. The Gatun locks are a 3-stage flight of locks, 2 kilometers long, and these locks lift the ships to the Gatun lake level, which is about 26 meters above sea level.
So, Nicole, that's about the same height as a 9-story building. Is that the right height that I'm thinking of?
Yeah, a floor is about 3 meters. So yeah, it'd be about 9 stories, which is actually, when you put it that way, it does seem quite high. When you look at 26, you think, oh, that's not that bad. But yeah, that is substantial.
And these are not small ships either, right? This is not, something that you and I could go float down the river in. Like, these are carrying hundreds, maybe thousands of shipping containers and international commerce around the world. Like, these are not small ships by any means.
No, these are huge ships. From the sounds of it, they basically almost fill the lock to the brim. They're kind of fill the entire, in some sections of the canal, when you look at the pictures, it looks like the boats have no room to move on either side. What it seems like they do for shipbuilding is they determine which routes the ship will likely take and what the biggest boat size those routes can handle, and then they build the ship to that max. So there's a boat size called the Panamax, and that's the maximum size of ship that can pass through the Panama Canal. And so that's kind of a limitation set on any ships that are intended to use this route, which I thought was really interesting. I mean, it makes sense, but I just thought that was interesting. So Gatun Lake is an artificial lake formed by the building of the Gatun Dam, and it carries vessels 24 kilometers across the isthmus. It is the Summit Canal stretch, fed by the Gatun River and emptied by basic lock operations. So with that lock, you need water to serve it. So you need water to fill it up as you're going up, and to somewhere to put the water as you're going back down the other side. And so I thought that was a really interesting solution by building this man-made lake in the middle. They're essentially using that lake as a reservoir to run the locks. It doesn't work perfectly, and they have had to make some modifications, which we'll get to run the locks successfully. But I did think that was a really interesting solution. So from the lake, the boats travel down the Chagres River, a natural waterway enhanced by the damming of the Gatun Lake, and that runs about 8.4 kilometers. The Culebra Cut slices 12.5 kilometers through the mountain ridge and crosses the Continental Divide and passes under the Centennial Bridge.
That sounds really cool. So you have this man-made cut that goes across the Continental Divide, which separates where rainwater goes to the Atlantic side or the Pacific side, and there's a big man-made channel that crosses that.
Yeah, interestingly enough, related to hiking, we don't live that far from the Continental Divide Trail. The northern part of it, at least, it goes right through Banff, I believe.
It starts in Waterton and it goes up to Banff and then up to Jasper.
Yeah, pretty cool. So that divide goes all the way down to, I believe, through South America, no?
Yeah, absolutely. It goes through South America, goes through Central America, basically runs the whole extent of the North American, South American, Central American continent.
Very cool. And I think the coolest part about the Continental Divide is that any water on the west side goes to Pacific, and any water on the east side goes to Atlantic. So that's a really interesting thing to think about when you're trying to figure out which way rivers flow. Anything in Calgary flows east or south because we're on the east side of the Continental Divide.
Nicole, did you know that there's also a triple divide point?
No, what's that?
So just like the Continental Divide, there's certain spots where the water will flow up into the Arctic Ocean. So there's one actually, again, not too far from where we live here in Calgary, up by Snowdome, I believe. And that separates the water that's flowing from, I guess, going to the Pacific Ocean and the Arctic Ocean and the Atlantic Ocean.
Oh, interesting. That's pretty cool. Water is a fascinating beast. So after the Continental Divide, the ships will reach the single stage Pedro Miguel lock. So as I said before, we've got 6 locks total. From the Atlantic side, there's 3 locks altogether, but then on the Pacific side, those locks are broken up into 2 separate stages. So the first is single stage, so 1 lock only, and that lock is 1.4 kilometers long, and it's the first part of the descent with a drop of 9.4 meters, so about a third of the way down. And then the boats will reach the artificial Miraflores Lake, a 1.8 kilometer lake, about 16 meters above sea level. And then there's the Miraflores locks, which are the 2-stage locks. And this section is 1.8 kilometers long with a total descent of 16 meters at mid-tide. From the Miraflores locks, the boat reaches Balboa Harbor, again with the multimodal exchange provisions. So the railway meets the shipping route again. And this is also near Panama City. From this harbor, an entrance channel leads to the Pacific Ocean or the Gulf of Panama. And this section is 13.3 kilometers from the locks. And it also passes under the Bridge of the Americas.
So the average passage time through the locks is 11 hours and 38 minutes. Like Nicole mentioned, there's a series of 3 locks weighing over 700 tons each that bring the ship 26 meters above sea level into Gatun Lake. The original locks were 33.5 meters wide. A third wider lane of locks was built between September 2007 and May of 2016, which opened in June 26 of 2016, and that allowed an increase in vessel length of 25%, a 51% increase in width, and a 26% increase in draft.
So as I mentioned earlier, there's a what they call a Panamax ship or a Panamax vessel. So the maximum boat length that travels through the canal is 366 meters long, 49 meters wide, with a draft of 15 meters. So these ships are just filling up the new width, the new section of canal.
Yeah. So there's over 14,000 vessels a year that transit through the Panama Canal, so about 4 to 5 a day on average for the entire duration of the year. And the tolls that Panama charges are based on the type of ship, the type of cargo, the size of the ship, and it's measured in TEUs, which are the size of a standard shipping container. And the going rate seems to be about $60 per TEU, although there's a whole bunch of other factors that go into that. So it's not a cheap passage to go through. But in terms of time and also money spent in fuel and money spent in time, it's so much cheaper than going around Cape Horn.
Yeah, and there's also some passenger ships that pass through the canal as well. That's not uncommon. And so they obviously don't have shipping containers on them. And so they have other methods of tolls. So there are a number of factors that go into how the tolls are calculated. The average toll is around $54,000. The highest fee for priority passage, so if you want to skip the line, it looks like, was about $220,000, and that was paid in 2006. The most expensive is $375,000, but the normal fee is around $13,000.
You can pay $400,000, and that guaranteed, like you said, you can skip the line, and it's guaranteed passage in no less than 18 hours.
So, fun fact, the lowest toll ever paid was 36 cents by an American, Richard Halliburton, who swam the Panama Canal in 1928. It's a long swim.
That is a long swim. But what if like a dime or a nickel fell out of his swim trunks and he couldn't afford the toll? Like that would be soul crushing. You're there swimming through the Panama Canal and you're like a nickel short.
He just swam 82 kilometers. I would just let him no toll. You just swim for free. It's impressive. Although I guess he's holding up a bunch of space for ships.
Definitely got his 36 cents worth out of it though.
Yeah, he probably did. So we're talking a lot about locks. What are those? So the locks are essentially chambers in the canal route that raise or lower boats between different sections of water at different elevations. So they're not the same as lifts where the chamber itself rises and falls. Essentially, the lock itself is a chamber the boats drive into, and then the gate closes behind them. And then they will either, if the lock is going up, they'll fill the chamber with water and allow the boat to rise until it's equivalent to the next section of the canal that it's flowing into, and then they'll open the gate on the other side and the boat will drive straight out. If they're going down, then the boat will drive into the lock, and then they'll lower the water. They'll remove the water in the lock until the boat lowers to the same elevation of its adjacent section, and then they'll open the other gate and the boat will drive out. So that's why it's so important for the ship size to fit within the lock, because if they can't close the lock gates, then they can't properly fill or remove the lock water, and so it just really doesn't work. The lock walls range from 15 meters thick at the base to 3 meters at the top. The gates are an average of 2 meters thick, 19.5 meters wide, and 20 meters high. So these are definitely some very large, heavy-duty gates.
All those dimensions just sound ridiculous, like 15 meters thick and 19.5 meters wide, 20 meters high of these steel gates that open and close. Those are really, really big.
Yeah, huge. So I've never seen a lock this size in action. I've never been to the Panama Canal, but I did grow up in southwestern Ontario, and there are some smaller locks there along rivers. And I remember being a small child and seeing them for the first time and I can't remember who I was with. It was my parents or grandparents, but I made us wait. I wanted to see a boat go through that thing. What is this? How does it work? Tell me everything about it. I think locks are just so fascinating.
Oh, they're so neat. My dad's an engineer, and as part of a science project when I was a kid, we built our own locks that, you'd have to fill them manually or drain them manually, but we were still able to bring a boat, up and down within our little lock system. And yeah, it was a really neat thing to see working.
Yeah, very cool.
So Gatun Lake in the middle of the Panama Canal Passage provides millions of liters of water to operate the locks. So it has impassable rainforest around the lake, and that's the best defense of the canal and remains mostly untouched by human interference. So it's hard to get to the lake. It's hard for people to interfere with the lock operation. 33 kilometers of the trip through the Panama Canal goes through or over Gatun Lake. It has a surface area of 425 square kilometers, and it also has a 5.2 cubic kilometer volume of water in the lake, and it also provides drinking water for Panama City and Cologne.
So interesting. Since the ships do go both ways through the canal, I mean, you can go from Atlantic to Pacific or Pacific to Atlantic. Opposite passages deplete and replenish the water in Gatun Lake. So that is kind of a wash to an extent. But the lake accumulates excess water during wet months and a shortage in the dry season. So to combat that and to handle the water depleting and replenishing as boats move through the locks, in 2016, when they did the refurbishment of the canal and they added a bunch of additional features and made some of the sections larger, they added 3 water-saving basins to each lock, which reuses 60% of the water in each transit. So these basins are essentially a holding tank, and as they pump water in and out of the lock, they take water out of that basin and put it back in.
That seems like a pretty efficient way to do things.
I think so. 60% though does seem a little low. But I mean, when you open the gates, you're losing a lot of water that way. So I think that there's some things that are a bit trickier to overcome. But I do think that was a really good add, I will say. The other option is that you're pumping water. I mean, you do have oceans on both sides. So in theory, you can pump water, but that's a lot of water to deal with. So I think this is a better option. And you don't have to use the power of pumping it. Also, an interesting fact, the mean sea level, so the average sea level on the Pacific side, is 20 centimeters higher than on the Atlantic side. And this is due to a difference in ocean conditions such as water density and weather. But I thought that was interesting. Even though all of the bodies of water do in theory connect, they're not all at the same elevation, which is just a fun fact.
The Panama Canal is not the only canal that's been proposed for Atlantic to Pacific commerce trade. A Hong Kong company has proposed a 280-kilometer canal through Nicaragua to transport materials from the Atlantic to Pacific or the Pacific to the Atlantic. However, there's a lot of opposition from environmental groups, and assessments are ongoing, and at least 30,000 people will be displaced by this project. Up in northern Canada, there's the Northwest Passage that, as ice caps melt more and more, the route is becoming more and more viable due to thinning ice.
Thanks, climate change.
Yeah. Thanks, climate change. Not really.
Just kidding.
There's also some rail projects that are being explored to bridge the two oceans, through Colombia, through Guatemala, through Costa Rica, through El Salvador, and also through Honduras.
One last thing we wanted to talk about the canal was that, as I mentioned, it's very tight and it can be challenging to navigate. There's not a lot of room for error. The ships pretty much just fit through the locks and through certain sections of the canal. There are canal pilots that you essentially hire when you're going through the canal. I would assume they're part of the toll fee. I would assume that they're mandatory.
They're definitely mandatory.
Yeah. So the pilots board each ship seeking passage and then captain it or drive it through the canal. So you pick them up on one side and drop them off at the other, which is similar to the harbor pilots in Tampa Bay that navigate under the Sunshine Skyway Bridge, or in some instances crash into the bridge, that we covered in episode 16. So we know a little bit about harbor pilots.
I bet you'd get really good at captaining a vessel through the Panama Canal if you were a pilot.
But yes, agreed. But would you not find it a little bit boring? I mean, you're just driving back and forth.
But there's a lot of different factors, too, that you have to consider, because every ship's going to steer a little bit differently. They're loaded differently. There's wind loading on things. Probably different things going on with the locks every time you go through them. I think it would be pretty interesting to be a pilot going through the Panama Canal.
So what do you think? They are based on one side, and then they get in on, let's say they're based on the Atlantic side, so they'll do one day, they'll go there, stay overnight, and then go back the next day. And then you think they're off, or do you think they do 4 trips and then off, or like, how do you think that works? I'm always curious about that.
I have no idea. It's a little bit less than 12 hours to go from one side to the other. So I would think that they'd go travel in one day and then probably take a rest day and then come back maybe the day after that. It would really depend on the traffic too, right? Because if there's more ships that go from west to east, then you're going to stack up your pilots on the east. So maybe some of them fly back or come back on the railway, or just double back on, essentially deadhead back from one side to the other side.
Oh, that's a good point. They could also swap them out at Gatun Lake, because that's kind of in the middle, which is another option. I would assume actually most of them probably live on the Pacific side, because that's where Panama City is. I would assume that's where, and then they probably have some kind of housing on the other side. It just, looking at the map, the Atlantic side looks less populated, or at least less densely populated.
But if anyone knows how canal pilots work on the Panama Canal, let us know through any of our social media channels.
Yes, please. If you're listening to this in Panama, we want to hear from you.
So there you have it, the Panama Canal, one of the 7 wonders of the modern world according to the American Society of Civil Engineers. Some lakes, channels, and 6 locks make up one of the most critical shipping routes in the world. And they made it over 100 years ago with a fraction of the tools we have today. It's beyond impressive and extra nerdy when you think about all of the problems they had to overcome and how they did it.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find it. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com, or you can connect with us on LinkedIn. Check out the show notes for links to all of these. And thanks everyone for listening. Don't forget to tune into the next episode of Failureology, where we'll discuss the transatlantic telegraph cable failure. Yes, the internet is hardwired. Bye everyone. Talk soon.